Hello, my name is Mekre Mesganaw, and I am an applications engineer for Texas Instruments' current and position sensing product line. In this video, we will discuss how 3D linear Hall sensors can be used to detect magnetic tampering in electricity meters, as well as the advantages of these 3D linear Hall sensors against other types of magnetic sensors. Although this video discusses magnetic tampering of electricity meters, the concepts here are applicable to other end equipment that desire to detect magnetic tampering as well. So to begin, let's start by asking what is electricity meter tampering and why is it such a problem? Electricity meter tampering is a type of non-technical loss where individuals hack meters to slow or stop the accumulation of energy usage statistics in an attempt to reduce their utility bill. Actually, tampering with a meter is one way someone tries to steal electricity. It is one type of non-technical loss. Non-technical losses in total, which includes electricity meter tampering, as well as other tampering methods, account for billions of dollars of revenue loss for utility providers. In 2017, a study mentions that a total of $96 billion are lost globally a year due to non-technical losses. This revenue loss not only affects utilities. The revenue loss leads to higher prices of electricity, which affects consumers as well. The large revenue loss due to non-technical losses is why utilities are interested in designing electricity meters to detect and prevent tampering. One of the most common ways someone tries to tamper with a meter is to apply a magnet on it. This magnet affects transformers in power supplies as well as current transformer current sensors.
To demonstrate how a magnet could affect the ferrite core transformer in a power supply, we measured the output voltage of the power supply. Here we see that it is 3.391 volts when each phase has 230 volts applied to it. Now we'll see what the reading is when we apply a powerful magnet to the power supply transformer. For this test, for safety reasons, we place a physically smaller magnet than one used for e-meters, but we place it closer to the transformer in order to better simulate the actual conditions of when someone performs magnetic tampering. Here we place the magnet on top of the ferrite core transformer. So we close the system up and apply the same 230 volts input from our source generator. If we look at the output voltage of the power supply, we see that it doesn't go up to 3.391 volts. In fact, it doesn't go above 0.1 volts, as you'd expect. And this is because of the effect of the magnet on the power supply transformer.
To deal with magnetic tamper attacks, power supply transformers that are magnetically resistant, such as powdered iron magnetic cores, can be used. However, this is only effective to a certain extent and is not completely magnetically immune. Cap drop power supplies, which are transformerless, can also be used as a magnetically immune alternative to transformer-based AC/DC power supplies. However, cap drop supplies have limited current drive, so they are not feasible for meters with power-hungry communication modules. Strong magnets can also affect current transformer current sensors.
To show the effect of magnetic tampering, we apply 230 volts, 5 amps, a unity power factor on each phase of electricity meter. To show the effects of tampering, we use a PC GUI that will display the active power readings of each phase. Here we see that approximately 1150 watts has been applied to each individual phase. Now we'll see how some of these values would change when we apply a magnet on particular CT. For this test, we applied the magnet on top of the CT for phase C. After applying the magnet, we then applied the same 230 volts 5 amp unity power factor conditions. Here we see that the active power readings have decreased for phase C from 1150 watts down to 43 watts. As a result, the consumer will be charged much less electricity than what is actually being used. That is all because of the effect of the magnet on the current transformer current sensor.
In this video, a physically small size magnet is used to show the effect of magnets on CTs. It should be noted that larger magnets cause a larger drop in readings. A strong enough magnet could even cause a zero current reading from a CT. In addition, multiple CTs could be affected by the same magnet, with the closest CT most affected by the magnet. One method to deal with the effect of magnets on CTs is to try to shield the CTs. However, CTs could only be shielded to a certain extent. In addition, shielding requires additional material and labor costs and undesirably increases the weight of the meter. Depending on the requirements of an electricity meter, it may not be possible to design a meter to be completely magnetically immune. Due to this susceptibility of meters to magnetic tampering, magnetic sensors are often used in electricity meters to detect external magnetic fields in order to take appropriate action, such as disconnecting services or applying a penalty fee for tampering. This sensing can be done with reed switches or Hall sensors. The advantage of Hall sensors is that they are not as fragile as reed switches, which may break during assembly. When using Hall sensors, traditionally 1D Hall switches were used to detect strong magnetic fields in 3 directions. Out-of-plane sensors detect the magnetic field perpendicular to the die. As an example, in this diagram we see a PCB located inside an electricity meter case. For this scenario, a surface mount out-of-plane Hall sensor on a PCB is best at detecting when magnets are placed above or below the case, as shown in the picture on the left. In order to detect a magnet in front or behind the case, a through-hole out-of-plane Hall sensor should be added and oriented as shown in the middle picture. Finally, to best sense when a magnet is to the left or right of the case, a through-hole out-of-plane Hall sensor should be oriented as shown in the right picture. In traditional magnetic tampering implementations used in electricity meters, 3 out-of-plane sensors are used together in order to detect magnetic tampering in all 3 directions. This enables fully detecting the different magnet-to-case orientations, as shown in the picture on the left. Each of these sensors are omnipolar, which enables detecting both north and south poles of a magnet. If any of the 3 Hall switches detect that the absolute value of the magnetic flux density is greater than the operating point spec of the Hall switch, referred to as BOP, the Hall switch asserts its output to indicate that magnetic tampering has occurred. The output stays asserted until the sensed absolute value of the magnetic flux density falls to below the release point spec of the Hall switch, BRP. The figure on the right illustrates the functionality for an active low Hall switch. When using Hall switches for magnetic tampering detection, Hall switches must be selected to have an appropriate BOP. The necessary BOP would depend on the distance from the Hall sensor to the magnet, which in turn is determined by the dimensions of the electricity meter case, and also the specifications of the desired magnets to be detected. If the BOP is too large, which is low sensitivity, the Hall switch would not be able to detect the presence of the magnet. On the other hand, if the BOP is too small, referred to as high sensitivity, false positives may be detected from nearby interference, which may lead to overcharging customers if penalties are applied for magnetic tampering. To help prevent false positives in this case, either a low sensitivity Hall switch can be selected or a medium to high sensitivity switch can be used with external shielding to reduce the magnetic flux density seen at the sensor. Instead of using 3 1D Hall sensors, an alternative approach to detecting magnetic tampering is to use one 3D linear Hall sensor, which has 3 mutually orthogonal Hall elements integrated into a single package, thereby enabling sensing in all 3 directions, the X, Y, and Z directions. In addition to one out-of-plane sensor, 3D Hall sensors also have two in-plane sensors integrated, where the in-plane sensor detects the magnetic field parallel to the die. Consequently, 3D linear Hall sensors can detect any magnetic case orientation with one surface mount IC, as shown on the left. 3D linear Hall sensors can therefore enable a more compact PCB layout. In addition, having a surface mount only implementation can reduce PCB manufacturing costs and has other manufacturing benefits compared to if a through-hole part is used. In this video, a magnetic tampering test is done on an example electricity meter that has the TMAC5273, which is a 3D linear Hall sensor. The resulting X, Y, and Z magnetic flux densities are graphed for the X, Y, and Z magnetic case orientations. In this video, we will demonstrate the TMAC5273 3D linear Hall sensor detecting a strong magnetic field in the X, Y, and Z directions. First, we apply a strong magnet on the top of the sensor, which corresponds to the Z-axis. Notice a decrease in magnetic flux density, so there is a large negative value. Then we flip the magnet to apply the opposite orientation. Now we see that a large positive magnetic flux density reading in the Z-axis as shown in the bottom graph. Next, we test the Y-axis and see that there is a large negative reading. We flip the orientation of the magnet again and see that there is now a large positive reading in the Y direction, which is the middle graph. Finally, we test the X-axis, which is the top graph. Notice when we apply a magnet, there is a large positive reading. We flip the orientation, and then there is a large negative reading for the magnetic flux density. This shows how the TMAC5273 can detect a strong magnetic field in X, Y, and Z directions. In the right picture, you see a magnet applied to an electricity meter in an attempt to steal electricity. To the left, you see the resulting magnetic flux density readings from a 3D linear Hall sensor. In the graphs, the sensed magnetic flux densities of the X, Y, and Z Hall axes in the Hall sensor are shown. Since the magnet is in the Z orientation and the case dimensions lead to a small distance from the magnet to the Hall sensor for this orientation, a large magnetic flux density of about 100 millitesla is seen at the Z-axis. Due to 3D linear Hall sensors providing information on the actual sensed magnetic flux density value, the magnetic tampering threshold of each axis can be selected to anything within the magnetic sensing range of the 3D linear Hall sensor. This allows customizing the magnetic tampering threshold based on the desired magnet and the dimensions of the meter case. In this example, you can select the Z-axis magnetic threshold anywhere from 0 to 100 millitesla and still be able to detect the presence of the external magnet. This type of flexibility is not possible for Hall switches with fixed BOP specifications, since there are typically only a fixed number of BOP options available for a Hall switch. In addition, many 3D linear Hall sensor devices can sense large magnetic flux densities as shown above, which allows setting a large magnetic switching point, if necessary, for preventing false positives. Since the 3D linear Hall sensors can detect large magnetic flux densities, additional shielding is not needed for setting a high magnetic switching point like it is needed for higher sensitivity, low BOP Hall switches. 3D linear Hall sensors can support switching between multiple power modes depending on if it is desired to reduce system current consumption. Power modes supported by 3D linear Hall devices often include an active mode for taking measurements, a sleep mode for minimizing current consumption, and a duty cycle mode that automatically switches between active and sleep modes. Active mode is used for taking measurements and takes the most power out of the different power modes. This mode is often selected when running off the meter's AC/DC power supply, since the relatively high active mode current consumption is negligible when running off this particular power supply. The sensor could then be put in sleep mode when it is desired to minimize the current consumption, such as in systems that do not require enabling magnetic tampering when running off a backup battery. In duty cycle mode, the device takes measurements and then automatically goes to sleep for a user-specified amount of time. Duty cycle mode is good for minimizing current consumption while still detecting magnetic tampering, such as when low-speed magnetic tamper detection is necessary when running off a backup battery. To reduce average current consumption in duty cycle mode, a long sleep time should be selected. The datasheet snippet at the bottom of the graph shows how average current consumption decreases when the sleep time is increased from 1 millisecond to 1000 milliseconds. When selecting the sleep time, please note that it should also be selected so that the sum of the sleep time and conversion time is less than the desired response time. As an alternative to wake up asleep mode, the MCU can manually set the sensor to sleep mode and then manually set the sensor to wake up mode after the desired sleep time has passed. This requires more overhead from the MCU. However, this option may reduce the system current consumption if the MCU is required to be in its own wake up asleep mode. Some 3D linear devices have the capability to enable setting an interrupt pin when the sensed magnetic flux density of any axis goes beyond its user-defined magnetic switching threshold. The picture shown here shows an example of this functionality, where the interrupt pin is set when the absolute value of the X channel's magnetic field goes above the user-defined XCH threshold. For electricity meters, the 3D linear Hall sensor should be configured to look at the absolute value of the sensed magnetic field when determining if the threshold has been passed. This is necessary to detect both the north and south poles of a strong magnet. Since the Hall sensor's interrupt pin can wake up the microcontroller when the microcontroller is in a low power mode, and since the microcontroller doesn't have to read the Hall sensor to determine when the magnetic threshold has been surpassed, the microcontroller can go to a low power mode when running off a backup power supply until it is woken up by the Hall sensor's interrupt pin. The interrupt feature and duty cycle power mode can be used simultaneously to reduce system current consumption and extend the lifetime of the backup power supply. AC magnets not only affect current transformers, they can also affect shunt and Rogowski coil current sensors. To detect AC magnets, a 3D linear Hall sensor can also be used. Detecting AC magnets requires a fast enough effective sampling period and a small enough sleep time to properly capture enough samples along a cycle of the AC magnet waveform, as shown in this picture. The effective sampling period corresponds to the time needed to get one set of samples, which is dependent on the internal sampling rate of the device and the number of samples that are selected to be averaged together to produce one effective sample. Since linear Hall sensors provide information on the actual sensed magnetic flux densities, they are more suited to detect AC magnets than low sample rate Hall switches. So to summarize, in this video we have seen the many benefits of using 3D linear Hall sensors. One of the advantages includes their ease of assembly compared to reed switches. In addition, only one surface mount IC is needed instead of the two through-hole and one surface mount sensor when using 1D out-of-plane sensors. This one surface mount IC enables a more compact PCB layout and reduces PCB manufacturing costs. Additionally, 3D linear Hall sensors enables the user to define where they want the tampering threshold to be for each axis. This is an improvement compared to most Hall switches, which only have a fixed number of BOP magnetic threshold options. Also, 3D linear Hall sensors typically have multiple device power modes that can be selected from based on the system current consumption requirements. To further reduce system current consumption, some 3D linear Hall sensors have a dedicated interrupt pin that can be used to wake up a sleeping microcontroller to alert it that magnetic tampering has occurred. Finally, 3D linear Hall sensors are best at detecting AC magnets, which could tamper with CTs, shunts, and Rogowski coil current sensors. All these features enable 3D linear Hall sensors to implement a flexible, compact, and low-power solution for robust magnetic tamper detection, thereby reducing the impact of electricity theft on utilities and consumers. If you would like to learn more about our Hall effect sensor portfolio, please visit ti.com/Hall Hall Effect to explore our technical resources and products.